So let's look at an example of free energy change. And we're going to use this example we brought up before, which is the thermite reaction, or a version of the thermite reaction. And it's a really simple reaction. It's just aluminum metal mixed with rust or iron oxide, and this produces iron. But notice the phase here is liquid, and that's because it's so hot. It creates molten iron and then aluminum oxide. And this is really commercially relevant because it allows folks who are assembling railroad tracks to do on-demand welding, because you can create liquid iron, and that allows you to join railroad tracks in the field when you don't have access to necessarily things like an acetylene torch or gas or anything to heat this up. And so you literally can bring out powdered aluminum and powdered rust, and you can get on-demand liquid iron. And they just create a ceramic mold around the rail section here, and you mix these things in the top part of this in the crucible, and when the reaction gets so hot, it turns this into liquid iron. It flows down in, and then it solidifies. So we talked about earlier, especially in the kinetics section, that this reaction, when you mix these things together up here, they don't actually just react right away. And that's because there's an energy barrier, an activation barrier, which makes the reaction incredibly slow. But the reaction, once it is proceeding, has a huge negative free energy change and enthalpy change, which is what liberates all of the heat. And I want to use the table of values here, these standard values, to do two things. I want to be able to calculate what the delta G of reaction is for the reaction as written, using just the typical free energy equation, so delta H minus T delta X. And I want to use the same table, but I want to use just the free energy of formation values to get the same answer, and they should be the same here. So let's start with the first one here, which is calculate delta G of the reaction using this equation, which means that we need to figure out what the free or the enthalpy change for the overall reaction is, and the entropy change for the overall reaction, both under standard conditions. And so with this table, if we want to figure out what the change in enthalpy is for the reaction, then we have all of the terms, right? And so really it's just summing up the products and then subtracting the enthalpy change of the reactants, and making sure you're multiplying by the correct coefficient in the balanced form of this expression. So we would start with the products here, so there's really just two entries. The two products are iron and alumina. We have two irons, 2 moles of iron, so 2 moles of iron times the 12.4, that comes from here, that's a positive value, and I'm going to add that to 1 times the Al2O3, which is minus 1657. So that is all of the enthalpy change in the products, and then from that we'll subtract the same process but for the reactants. So there's 0 for aluminum because it's in an elemental state, and then 1 times minus 824 for iron oxide. So we can tabulate this value. That'll give us delta H of reaction, so that term, and we can do the same thing for delta S and then solve this. So that looks like it gives us a value of minus 826.7 kilojoules. Notice this is not kilojoules per mole, this is just kilojoules for the reaction as it's written. So technically that would be minus 826.7 kilojoules per mole of aluminum oxide, or per 2 moles of iron. That's how we would interpret that. But that's the delta H reaction. So let's tabulate delta. So that gives us a negative entropy change, which is not something we're after here. That's not a favorable thing for the system, at least as it relates to this expression for free energy. Notice though that entropy is always in units of joules per mole Kelvin, because it's usually a much smaller quantity instead of the kilojoules per mole of the enthalpy change. So when we tack these values into this overall expression for delta G, we need to make sure we're careful about our units. So let's take these two numbers, pop them into the expression, see what we get. So I just rewrote this expression here now in terms of the quantities delta H and delta S that we computed. So it's minus 826 kilojoules minus 298 Kelvin. That's the temperature we're trying to compute this at. Minus 23.62 times 10 to the minus 3, because that puts me in units of kilojoules, which I should have written here. kilojoules per Kelvin. So the Kelvin here goes away, and then we're left with subtracting kilojoules from kilojoules, which is what we... That gives us a value of minus 19.7 kilojoules for the reaction as written, which would tell us that this is a very spontaneous reaction and an exothermic one. And so it will react on its own without energy input from the universe, and it will liberate a lot of heat, which is why it's useful for the applications it's found itself in. But as we mentioned before, these things actually won't react with each other at an appreciable rate because of that very high activation barrier. And so if you were to sketch this out based on what you know, you probably think that the reaction progress diagram would be something like this, where there's a very steep decrease in energy from the reactants to the products, but because it's really slow, you would assume that it would look something like this, where there's a fairly large activation barrier. And to get over this activation barrier in the field, they just bring a small torch with them, a little pocket torch, and they take these powdered things and they just add some heat directly. That increases the energy of these reactants such they can get over the barrier, and then once they're over the barrier, the reaction occurs very quickly and spontaneously. Okay, so the second question then is getting at the same exact value but by a different means, and in this table we also have the free energy formation under standard temperature pressure for each of the compounds in the system. And so we know that the sum of the products of these quantities minus the sum of the reactants is going to yield us the change in free energy for the particular reaction as written. And so I started this, but I'll let you finish the computation here because it's really just number crunching at this point. But the important concept takeaway here is that these quantities are exactly the same, but they're being derived two different ways. One way is using information about the enthalpy and entropy of the system. The other is using information about the free energy of formation of the individual compounds. All energy is conserved, all energy is the same in the system. These are state functions, so it doesn't matter how we get there, but the value, the difference in the energies of the products and the reactants should always be the same.